And so we'll bring up the slides here, and then we'll hear the speaker over the phone.
Do you hear me?
Yes.
Good, we can hear you, yes.
Okay, great. Hi, everyone. I have reflection. I hear my own voice.
Go ahead and mute, if you could mute your speakers, that would help.
Okay. I'm a postdoc at Space Science Lab, UC Berkeley. I'm Iranian, and because of my nationality, I was not permitted to join AIMS and physically join you guys for this meeting. And this is the reason I'm giving my talk virtually. I present a part of our latest research on the solar plus interaction with Quasimodo's lunar magnetic anomaly. First, we would like to know why this is important. By the great introduction by the previous speaker, Jan Deka, I think he almost covered all of the introduction I wanted to tell you now. But anyway, first of all, the interaction between the solar wind plasma and lunar crustal fields is different from that of a planetary magnetosphere. This is mainly because the spatial scale of lunar crustal fields is an intermediate scale between the solar wind electron and the ion gyroradius. Second, one of the proposed theories that discusses formation of lunar swirls explains a high degree of correlation between the presence of crustal fields and lunar swirls. And here, this figure from Hood et al. 2001 shows lunar cross-sector magnetic field observations of perhaps one of the strongest lunar magnetic anomalies located at the Cerizium antipode near the Quasimodo crater, known as Quasimodo magnetic anomaly. The locations of swirls like albedo markings are shown in yellow here, and the contour line shows the magnitude of the magnetic field. This is an example of correlation between swirls and crustal fields. This suggests that the lunar surface is shielded by crustal fields from solar wind plasma bombardment. You heard from Amanda talk about the correlation between the fields and the swirls, and in the next talk by Andrew Poppy, you will also hear a lot more about the connection between crustal magnetization and swirls. The general physics of the interaction is shown in this figure from Saito et al. 2012. As the solar wind plasma starts interacting with crustal fields, magnetized electrons reflect at higher altitudes while heavy ions penetrate deeper into the magnetic anomaly region. This forms a charge separation and results in formation of an electromagnetic field, electrostatic field over the magnetized areas that decelerate, deflect, and reflect ions above the crustal fields. Kaguya and Chandrayaan-1 satellite observations show that on average about 10% of the incident solar wind proton flux is reflected in charged form over the crustal magnetic field, but over some strong fields, the reflection can exceed over 50% of the incident flux. The figure here on right from Fontana et al. 2013 shows Chandrayaan-1 estimates of electrostatic potential around Quasimodo magnetic anomaly. They estimated an electrostatic potential of about 20 volts over Quasimodo magnetic field. Apart from observation, theoretical and numerical models have been used to study plasma interaction with lunar magnetic anomalies using MHD, PIC, and hybrid simulations. You did see from Jan Deka's some of the PIC simulation results. However, in these models, single dipole has been mostly used, except some of the MHD studies that multi-dipole approximation have been used. But we know today that the plasma interaction with lunar magnetic anomalies is a kinetic problem, and we also know that the lunar crustal fields are non-dipolar and they have complex field structure. Therefore, it's very important to take into account the actual structure of the crustal fields. Here we use a three-dimensional self-consistent hybrid model where ions are kinetic particles and electrons are a massless fluid. We include an empirical model of lunar crustal magnetization developed by Prucker and Nicholas 2010 into our model. The empirical model is a spherical harmonic model based on lunar cross-sector observation and is the highest resolution map of the internal magnetic field of the moon that is available today. On the figure on left, you can see the results of the empirical model of Prucker and Nicholas 2010 showing the lunar crustal magnetic fields in the far side at 30-kilometer altitude. And on right, you can see the Grazimovich magnetic strength at 20-kilometer projected into a plane. And this is what we apply into our model. It seems that I faced to a connection problem. Okay, came back. Before I present my simulation results, it's important to explain the coordinate system I use in my simulation. So here the figure shows the different planes show the different the magnitude of the Grazimovich crustal fields at different altitudes at the surface, 10 kilometer and 30 kilometer. In the coordinate system, we use the plus x-axis is normal to the surface of the moon. The plus z-axis points to the north polar axis, and the y-axis completes the right-handed coordinate system. The solar wind flows along the x-axis, so it's always normal to the surface. And the upstream parameters applied into our model are listed at the top of this figure. This figure shows Grazimovich magnetic fields, as I said, and we are mostly interested not only to understand the general physics of the interaction, but also we want to examine the effects of dynamic pressure on the course of the interaction. Therefore, we prepared 3 different simulation runs, one with the typical solar wind dynamic pressure that we call it the medium run with 1.2 nanopascal dynamic pressure, and one with lower and one with higher dynamic pressures. Here I only show the detailed results of the medium dynamic pressure run at 3-kilometer altitude above the surface. If you're interested to see more details, you can see and go read the published paper we have on this studies in JGR space. In all these panels shown here, the solar wind is pointing into the plane. The top left shows the undisturbed crustal fields. The top right panel shows the total magnetic field. That's the crustal fields plus solar wind fields. We see that the crustal fields are compressed and disturbed by the solar wind. The panels in the middle show the moonward going or down-going proton velocity and density. The contour lines show the strength of the magnetic field. We see that the solar wind velocity is decreased over the crustal fields, and the density plot, that's the right panel in the middle, shows that the solar wind protons are deflected around the crustal fields, around the strong crustal fields. The bottom panel shows that the downgoing proton flux is decreased by about 50%, so the crustal fields are shielding the surface from solar wind plasma. And the bottom right panel shows that the flux of the reflected protons moving away from the moon, we see that the reflected flux is about 10% of the incoming solar wind flux, which is consistent with the observations. And the results I'm going to show you in the next slide are obtained by averaging the fields over the white dashed circle I'm showing at the top on the top left panel. The top panel shows the average magnetic field strength and compares the results for low, medium, and high dynamic pressure. Undisturbed crustal field strengths are shown by dashed lines for reference. We see that the crustal fields are compressed and disturbed by the solar wind as a function of distance from the surface. The magnetic fields get stronger close to the surface when the dynamic pressure increases. At the bottom, we compare the electric field from the 3 different simulation runs. This electric field, which is pointing away from the moon, starts decelerating solar wind from nearly 50-kilometer altitude, we see that the field for low dynamic pressure is not as strong as that for high dynamic pressure. Our simulations show that the solar wind photons during low dynamic pressure are mostly deflected around crustal fields, while during high dynamic pressures, if the dynamic pressure does not push all the crustal fields down to the surface, they reflect the ions back to the space. On average, a potential of nearly 300 volt forms at the surface under the Grazimovich crustal field, which is, again, consistent with observations. Here, this equation shows how we calculate electric field in our hybrid model. Our electric field contains three different electric terms: a convective term, a convective term, Hall term, and ambipolar term. Previous work suggested that the Hall term is the dominant electric over the crustal fields. Our simulations here show that the ambipolar electric field that plays an important role on reflecting plasma has a noticeable contribution to the total electric field at close distances to the moon. Here, I think there was a delay. To sum up, we presented the first local hybrid simulations for the solar-wind interaction with realistic lunar crustal fields. We showed that the incident solar wind flux to the lunar surface is considerably reduced over the crustal fields, and the charged particles get deflected by the crustal fields. Here, the figure which is from our latest article, and now is the cover page of the current issue of JGR Space, shows a fountain of reflected protons from Grazimovich magnetic anomaly. We explained the effects of low and high solar wind dynamic pressures on the interaction. We discussed that during the low dynamic pressure, the plasma gets mostly deflected, but during the high dynamic pressure, they are mostly reflected back to space. And we also saw that the anti-moonward Hall electric field is the dominant electric field, but the ambipolar electric field has a noticeable contribution to the electric field at very close distances to the moon. So I should end up here.
Questions for the speaker? Anybody have a question?
Peter Chi of UCLA, interesting result. I think my question is simple. That is, how do you think about the modeling results and the differences from the previous presentation in terms of the particle reflection?
Well, there are two different models. The previous model is a peak model. They do have the electron dynamics included in their results, which we don't, or we partially do have them. But the major difference between this result and the previous ones is that we have included realistic fields from lunar prospector observations, as it's shown here. We have taken this map and applied it into our model. So the general difference would be, well, first, it's a localized interaction with a local crustal field. And the other thing is that when we compare, for example, here, we can see all the details. Let me see if I can turn on my pointer. Yes, here on, for example, the density plot, we can see all the detailed structure of, for example, that how the plasma would impact on the surface and would have the direct impact on surface weathering. That, for example, using a single dipole or multi-dipole does not give us the whole detail of the interaction.
Okay, great. Thank you. I think in the interest of time, we're going to move on. But thank you very much for calling in Shahab?
Yeah, thank you.
Okay. So the next talk in the session is